Next, we're going to work through approximate solutions for the Schrodinger equation. Looking at the case of finite potentials. And if we think about some arbitrary potential like this as a function of x, this might be u of x. Clearly the Schrodinger equation is a little bit more complicated than what we've dealt with up till now. Because we have this potential energy term. So it's a differential equation. This is a little bit more of something to manage. If the potential energy is 0, remember that we had life being somewhat simple because this middle term right here is 0, and our differential equation reduced to this. A second derivative of psi equals minus k squared times psi, where k squared is defined as 2m e over h bar squared. That's a rather simple case because then we have solutions for the wave function that look something like sinusoids. A constant a times e to the I kx plus a constant e times e to the minus I kx. In other words, when I take the square root here, I have a plus or minus sign for k. Remember that k has the physical significance of being 2 pi over a wavelength. So the larger the energy of the particle, the smaller the wavelength, and vice versa. So this is the easiest case, but it only works when the potential energy is exactly 0.